Hi there. Having reviewed sort of the introduction to powers and exponents, this lesson is about irrational numbers. And actually, there's two things about this lesson that I wanted to go through. One was the idea of getting you guys to use critical thinking, logical thinking, basically thinking mathematically to come up with some ideas. It's one thing just to answer questions out of a textbook, but a whole other thing to actually do some critical thinking. And this is sort of maybe the first exposure, well, maybe not the first exposure, but in our class anyways, one of the first exposures to try to figure out things and thinking mathematically. That's one part. The other part about it is to get a better understanding of why irrational numbers are called irrational numbers. So to begin with, what we start with is sort of an easier sort of process or exercise to go through, and that's to deal with the idea of bases raised to the power of 0. So the idea here is to be really methodical about how we go through this. So the first question is, what is the value of 5 to the power of 7 over 5 to the power of 7? So I think we would say this. It's similar for 8 to the power of 3, and even c to the power of 12 divided by c to the power of 12 would be 1 for any value of c. So what is the value of any number divided by itself is 1. Now the next question is, apply the common base rule dealing with exponents and division. 5 to the power of 7 divided by 5 to the power of 7 should equal 5 raised to what power? So that's this idea that we have 5 to the power of 7 over 5 to the power of 7. So we're going to use the Quotient Exponent Law, which we did last day. That's equal to 7 minus 7, which equals 5 to the 0. And we can do the same thing for c to the raised to the power of 12. So that's equal to c to the 12 minus 12, which is equal to c to the power of 0. And that number, we've already said is equal to 1. So that's a justification for why anything raised to the power of 0 is 1. So I know some of the students said, well, I know that c raised to the power is 1 because my math teacher last year told me so, which is fine, but now the idea is now you have a way to justify it to someone else. If someone else asks you why, perhaps you could go through this explanation and show them. Alright, the next one is, I think, more interesting, and it starts off with this statement. If square root of 2 can be expressed as a ratio of r over p of two whole numbers, then this fraction can be put in lowest terms. Assume that this has been done. So what we're saying is essentially we have the square root of 2 and it's going to be equal to two whole numbers as a fraction. That's the beginning statement. Next, you are asked to square both sides of that equation. So that's like square root of 2 squared equals r over p squared, and that's equal to 2 equals r squared over p squared. Fine, no problem. Next it says multiply both sides of the new equation by p squared. Alright, so let's try that. So maybe I'll start a new one over here. So I'm going to go p squared times 2 equals r squared over p squared times p squared. That's the algebraic idea that whatever we do to one side of the equation we have to do the other. So that gives us 2p squared equals, that cancels out, equals r squared. Okay? And then it says the resulting equation tells you r must be an even number. Explain. Well, for any value of p squared, r squared is 2 times p squared, and any number times 2 is going to be even. I'll say, and any number times 2 is even. Okay. So there's our explanation of why r squared is even. Okay, so if r squared is even, that means there has to be two things multiplied together that are even, and there has to be a 2 in there. For something to be even, there has to be at least one 2, and for it to be a square, it has to be at least two 2's. So it's 2n times 2n, or n could be anything. So if you take the square root of that, you get r is equal to 2n. So once again, any number times 2 is going to be even, so r must be even. Oops, must be even. Alright, next. Because r is even, its square is divisible by 4. That's kind of the same argument. If I have, if r is some 2 times n, r squared must be 4 times n squared. Therefore, r squared is, I'm going to run out of room there. Therefore, maybe I'll write down here. I'll have to use some arrows. Therefore, r squared equals 4n squared, and r squared is divisible by 4. So check. That's the explanation there. Alright, we're getting there. D, now we're at D. It follows then that p squared is even, hence so is p. So we have 2p squared equals r squared, and we're saying that 2p squared is equal to 4n squared. So p squared is equal to 4n squared divided by 2, which is equal to 2n squared. So this tells us that no matter what n squared is, p squared is 2 times that. So p squared must be even. Must be even. And then we can say use the same argument as before with the r. If p squared is even, then p has to be even. So that leaves us with a couple statements here. R is even and P. Actually, I'll just write that here. R is even, P is even. And we're told actually that explain why this is a contradictory statement situation. So we have this, R is even and P is even. And here's the contradiction. We started off with this idea here that we have a ratio of R and P. So R and P are two whole numbers, and it's put in lowest terms. It is impossible to have a fraction in lowest terms where both R and P are even. So for example, if R is some value 2 times n, and P is some value 2 times m, so R over P equals 2 over n over 2 over m. Clearly that's not in lowest terms. This can be reduced. So that's the contradiction. And that's what makes this so kind of interesting and actually irrational. We start off with the statement and we use pretty simple math to work out that R and P are both even, but that comes back and contradicts the original statement. The original statement is not true anymore once we say that. So it makes no sense. It's irrational. So that's what we could kind of say there, is that irrational because there is no ratio of R and P that can represent this situation. There's some other things we can say about irrational numbers. Irrational numbers do not repeat. Rational numbers do not repeat, and rational numbers can be represented as whole fractions, fractions with whole numbers. Alright, and then there's some practice questions here you can try. Just to kind of give a couple of really quick examples. 1.5, say, is rational. Why? Well, we can say that's 1.25 over 1 is equal to 125 over 100. So there, we've just represented 1.25 as a fraction of whole numbers. We can say the square root of 9 is rational because the square root of 9 is equal to 3, which is, say, 3 over 1, or 6 over 2, or whatever we'd like. What about square root of 5? It is irrational. There's just no fraction that can represent that. Okay, that's it for this lesson.